Okay, so we'll just make a start. This is what I was hoping you would have read last night, really, which was this first part of predicting. The other things you don't need to have done now, you've got a week to try and do those things. I just wanted to say a little bit about this and show you the next stuff. Yeah. Trying to explain what we mean by a model. If you've read through this, that's what it's about. It's trying to explain what we mean by a model, and it's also trying to get you to understand the terminology that's used when you talk about modelling. Actually, often when you're doing any bit of science, you're usually using a model of some sort. So there's a gradation between things you might not regard as a model through to things that are. However, when you're working in environmental science, it's explicitly about modelling, so you're dealing in those specific terms. We'll go through those briefly, and then the exercises that I just want to point you at are exercises that you can do that are they're related to the sorts of jobs that you do working in environmental science, but also in doing them, I want you to consider them in these terms. By these terms, this little cycle of producing a model is really the cycle of doing a bit of science, actually, quite often. It's coincident with the cycle of doing a bit of science. But the exercises that you're going to do, think about them in these terms. So the last thing it says, again, I'm repeating everything that's on here. There's the last thing it says here. Consider these exercises: compartmental modelling, groundwater modelling. Separate the tasks carried out and completing these exercises. The process is made explicit in Figure 1. That's Figure 1. So hopefully you've read through this anyway, but let me just point out a few things, particularly because words in boxes, if someone's going to set you a multiple choice or short answer test, then things that appear as words in boxes are pretty good things to have as questions on. So knowing what these words mean is quite useful. So the process then really is you start off with the real world. In order to construct a model of it, you have to make abstractions and assumptions. You make your abstractions and assumptions that allow you then to produce a conceptual model. It's important, you'll hear conceptual model used quite a lot. Geography students use conceptual models a lot. We don't think much of geography students. Right. Why? What's the problem with conceptual models? I think you read, it's probably written there behind you anyway. Conceptual models. When you see conceptual models, they're nice. When you go through a textbook and there's a nice block diagram with some lines on it, quite a lot of lines pointing here and there. That's a conceptual model. And the problem with conceptual models is that they're not formulated mathematically, which means that you can't put data in and get data out. If you can't put data in and get data out of them, it means you can't actually test the model. In lots of ways, that's brilliant. That's why geographers like conceptual models, because if you can't test it, you can't show that it's wrong. But actually, in terms of being useful, conceptual models are not actually necessarily that useful. Okay, and that's why you have to go all through the rest of this. And this is where, if you're working for a consultancy, or something complicated, this is where you start to use mathematicians. We're going to do a little bit of this, and I want to recognise what we're doing. Many of you engineers, and you'll find some of it's quite simple, but just recognise it as this process. This formulation, to formulate your conceptual model mathematically, requires some mathematical understanding. And then there's this big chunk of mathematical understanding that goes on here, which is the solution part of that. And what I can add to this, which maybe isn't written on here, is that typically the conceptual model is formulated, the formulation of it is you formulate it as differential equations, sets of differential equations. Typically what you regard as being a model if you work in environmental science. And then, when you've got a set of differential equations, you need to solve them. And solving them, differential equations that govern the way that environmental systems work are actually usually insoluble.
Differential equations in the mathematical model?
Yeah, typically, there's lots of examples where you don't use differential equations. It's just if you were talking to some hardcore environmental scientists, they might say it's only a model in their eyes if it's got differential equations in. Okay, but a map is actually a model. You can make a good argument that a map's a model. You're going to do linear regression, and linear regression is a model as well. It doesn't have differential equations in it, but it's still a model. But I'm just saying, when you're out there working professionally, then typically the models, when people talk about models away from academia, there'll be things that in the middle of them are differential equations, and the sorts of differential equations that govern environmental systems are ones that you actually can't solve. And it's not because we're not good at maths, many of you are. It's not because we're not good at maths, it's just that you can't solve them, the ones that govern environmental systems. So they can only be solved under very special conditions. And for those of us that are less good at maths, this is a good thing, because we don't have to do the hard maths to solve them, because we can solve them using a computer instead. And that's why mostly these things are solved. There's a computer solution for them. The computer solution generally means breaking down, we've talked about this briefly already, breaking down time into small pieces, breaking down distances into small pieces, so you're no longer dealing with differential equations. Differential equations effectively model continuous changes, but what we do is break them down into difference equations which model small changes one after the other. You're going to do examples of this, so it'll become clear for anyone it's not clear to, but I'm just telling you what's going on when you're actually going to do these examples. This is what you're looking out for. And these steps then, the solution that you use, if the solution does use a numerical method, these are the terms that you use. Computer solutions are often called numerical methods. Okay, a numerical method is an approximation, effectively. And as an approximation, it requires verification. Right? This, it's all on the videos as well, so don't worry, you'll get this again and again. But I'm trying to excite you a little bit here, because there's a link here, right? If you use a computer solution to your set of differential equations that govern an environmental system, then inevitably that computer solution, the numerical solution, is an approximation. Like, you've heard something like this before. What was the last thing we were talking about that was an approximation? It's only yesterday and the week before. Well, help me out. What were we talking about? What's the type of the course? What's the first word in the title? Yeah. Any measurement is actually an approximation as well, isn't it? Because the measurement you make is always a sample of the whole population of measurements. So we recognise that any measurement we make is an approximation. But what do we do about that? Because we've recognised it, we don't just tell someone what the measurement was, do we? What else do we tell them? Come on, you should all shout it out. Yeah, we need to tell them how good the measurement is. And it's exactly the same with this as well. If you use a computer solution, you know it's an approximation. Because it's an approximation, there's no point telling them the answer unless you also tell them how good or bad an approximation it is. So that's vital. So the good news for all of this is that, well, for the engineers, maybe not such good news because you've spent years learning how to solve partial differential equations. But for those of us that haven't spent years trying to solve partial differential equations, the good news is that you generally don't have to, because you use a computer solution for them. The little bit of, not bad news, but the little bit of hard work that you do have to do is if you do use a numerical solution, a computer solution, you not only have to give the answer, but you also have to give some comment on how reliable the answer is. That would apply for the whole of your model. There's problems with your model because of the abstractions and assumptions, but also if you use a computer solution, there's something about the reliability of the model that comes from the approximation that's carried out in your numerical method. And so, giving some idea of how good the answer to your mathematical solution is called the process of verification. It's important you understand what that is. A lot of people that have gone out from here and got their first job working in environmental science, their first project will have been verifying models. Okay, so it's good to know what this means. If you're not clear at all, it doesn't matter, because you're going to do 2 exercises at least that it says it over and over again quite clearly. But I just want you to see that connection. You know, we've got, if you make a measurement, it's an approximation. If something's an approximation, if you know it's an approximation, there's no point telling someone an answer unless you also tell them how good an approximation it is. And that also applies to this little part of this cycle. Now, sometimes you don't use a numerical solution. Sometimes you can have an analytical solution. An analytical solution is when you can solve the mathematics analytically, and then you don't need to carry out verification. But just recognise the difference. Okay, and then you get your output. The output then, you compare it to the real world. Comparing it to the real world is the process of validation of your model. So you're validating to see whether your output from the model matches what's seen in the real world. So it's validation. But also this process of calibration. There's 2 things that could go on. You can see, does it match to the real world? If it doesn't match, there's 2 things that you could do. One is you could try and calibrate the model. Calibrating the model means changing some parameters in the model where you know that those parameters aren't completely defined. So you've got to have some justification for changing them, but you can change the parameters, and that's the process of calibration. Again, there's an example of this. It's a very, very simple example, but it takes you through each of these steps so you understand what we mean. Okay, so you can calibrate the model, but sometimes, however much you calibrate it, however much you change the parameters, you still can't get the output of the model to match the real world. At that point, you have to go back to your abstractions and assumptions. That tells you that your overall assumption about the model is wrong. So there's an example that you're going to have a look at, which is looking at the way that rainforest regrows and seeing whether it fits a logistic model of growth. So your abstractions and assumptions about the way that a rainforest regrows is that the only limit on growth is the control on growth is the size of the population, and eventually there starts to be a limit on growth because of nutrients or something like this. But initially, there's the only limit, the control on the population size is the size of the population itself, and then eventually it starts to become limiting. And that produces what I'm sure you've seen before, which is a standard logistic curve, an S-shaped curve. To get to that idea of an S-shaped curve, which is you get a population that increases really, really rapidly, and then population increase starts to slow down as it starts to approach its carrying capacity, you're making abstractions and assumptions in order to say this is the way the population will grow. Okay? You can take those abstractions and assumptions and you can formulate them mathematically. You'll do that in this exercise. You'll come up with the formula for logistic growth, and then you can use the formula for logistic growth to get some output. There's no need to verify that because it's an analytical solution, not doing a computer solution. You get the output, you can compare it to the real world where you've got some data, and you can see whether your model of logistic growth fits the real data. Now, there's parameters in the model. In the same way that in the normal distribution, the mean and the standard deviation are parameters that control the shape of it. The logistic curve, the shape of it is controlled by the growth rate and the carrying capacity. So the carrying capacity controls how high it goes up, and the growth rate controls how steep it is. So you can change the carrying capacity and the growth rate a little bit. You've got real data which you're using to derive the carrying capacity and the growth rate. So you can't change it a huge amount, but because it's real data, you haven't got an exact number for the growth rate. You've got a number with effectively an error on it. So it's all right to slightly, I'm doing this because in the old days when you had radios, you would move the dial and make what on earth is this guy doing? Well, in the old days when you tuned the radio, you turned the knob. Okay, get out of the station. Anyway, and you can try and calibrate it to get the curve to fit. One of the things, in order to get the curve to fit, you've got an idea of what you mean by goodness of fit. So there's also a little test of goodness of fit. So you're trying to improve the goodness of fit, get it as good as possible, but at some point you can't do any more than that. And you might find you can't get it to fit. In which case the calibrations fail, and what you need to go back to is your abstractions and assumptions. So your assumption that the only control on growth is the size of the population may be wrong. So you can see, if you're a scientist, then having a model fail because you can't calibrate it, but it fails because your assumptions, your fundamental assumptions are wrong, is really exciting. That's a great big hole for research, which again is the sort of thing we're looking for. That's a big hole for research. More likely, you're going to do a bit of research that allows you to better calibrate the model. So the sorts of parameters that go into it. We're going to talk about movement of contaminants through the subsurface. It's quite a big deal here. The models there, the fundamentals of the models are fairly well established, but what needs more research is the calibration, so the tuning of the parameters in the model. So the sorts of parameters would be how much tetrachloroethene sticks to biotite. So how much of a particular contaminant sticks to a particular mineral, and that's a parameter that you can tune in the model. But but you can do research just on that, and then that can sit in the model. So to give you an idea of where your research is likely to sit, given that you've got 3 months to do your projects, then you're more likely to do a piece of research that is going to be relating to something that would be a calibration in a model, rather than something that's going to deal with blowing a whole model out of the water and starting with something else. Okay. What's in this section is really what's going to occupy us for the rest of the time. And there's also another exercise which I'm just finishing off for you as well, which is specifically to do with groundwater and contaminants as well. But what I should say is there's a load of exercise and stuff that you've yet to look at anyway, because you've only had, whatever it is, overnight since I spoke to you last. So you've got a lot of stuff to look at. But it's not all in the text. Okay, so let me just review for you. Right, so you don't just go back. Right, so this, which is the example that you can work through, which is drawing standard errors and also designing an experiment, so you're controlling variability and just being explicit about controlling variability. All of these things you should do, but I appreciate that people work at different speeds, so you might not do all of them, but people that work faster, there's stuff there for you to do. This, I'm not going to ask you any questions about this in the test. Okay, so I don't want you to feel overburdened with loads of stuff you need to do. I want you to do as much as you can. I want you to learn as much as possible. And I don't want you to worry about what's in the test. I'm telling you, like this exercise, which, you should do it. But don't worry, it's not in the test. I'm not going to ask you any questions about that. this the main thing, this spreadsheet though, all the tabs on that student height spreadsheet, you do need to complete that spreadsheet. Like things that are on that spreadsheet will be in the test, so you need to make sure you complete that spreadsheet. Yeah, you do need to calculate the probability of 7 foot tall student, or if I want to ask you the likelihood of an 8 foot tall student, just know how to do that. And the thing is, you've got your spreadsheet set up, you'll do it by setting your spreadsheet up. It's an open book thing, your spreadsheet's there, you change it from 7 foot to 8 foot, and you get an answer. So, make sure you've done that. This stuff is all on that spreadsheet. Largely it's completing that spreadsheet. You do need to know how to propagate errors as well. Again, the best thing is if you've done one example and you've got it set up as your spreadsheet, then it's easy enough to do another one. And it's similar with these exercises as well. Let me just quickly go through them, then I'll tell you which is the one that you should do all of them, the progression of exercises. And there's time for you to do all of them, but if you feel there isn't time, then I'll tell you which one it is you really have to have got done. I don't like doing it because it doesn't. You should do them really. I try to make it so there's enough stuff to fill your time. But if some people are just different backgrounds, work at different paces, so you don't need to worry. Anyway, look, this set of case studies, if you like, are moving from what you've done so far is effectively a little research project that relies on being able to tell the difference between things. Okay, it's as simple as that. Very good research projects that do just rely on that. There's lots of work you can do on that. There's geomicrobiology projects where you'll be looking to see how much iron hydroxide is converted to magnetite under these different conditions. You've got 6 sets of conditions. You measure how it's converted. There's a lot of effort goes into making the measurements because you're using particular instruments or that. However, really, the thinking, the analysis part of it is just to be able to see whether you can see if something's different between treatment A and treatment B. And largely you might do that just by taking the means and putting error bars on them, plotting them, seeing if they're different or not. Okay, very good project, but it's just relying on that. The next grade up is, we've got number 1, studies involving comparison of measurements. 2, involving the relationship between 2 variables. So there's lots of studies that you might do that like this. So instead of seeing this one thing different to another, you might look at the relationship between one thing and another to see how related are they? Are they related? Under what conditions are they related? And this comes down to looking at correlation and regression, which is something you have done before, but there's an example of it here where it's worked up into a project. And particularly important is that you do the correct statistics with that. So this is a hydrological project. We're looking at the relationship between the concentration of solutes in water. The solutes might be contaminants, they might be nutrients, but the solute concentration in water in a river and the amount of water in the river. So what's the relationship between the discharge and the solute concentration? And it's an investigation into what that relationship is and what controls the relationship. So I don't want to say the word statistic. The experimental design really is to compare one thing with another and look at how good the relationship is and what controls the relationship. So in this case, well, it's really, again, it's all there, so I don't want to, it's best to just go through it. But it's allowing you to understand what's going on in the environment, in as much as there's two components to the solute mode in a river. So in a river, the solids that are being carried can come from either the atmosphere in the rain, or they can come from the ground. Okay. If you measure the total solutes in the river, you plot that against discharge, what sort of relationship do you expect to get? What do you think happens to the solutes in a river when you increase the discharge? Okay, we've got a graph then with solute concentration and discharge. What's the line going to look like from there? It could be, give me any answer. If there's, all these different things can happen. So you think the concentration is going to increase with discharge? I think it's going to decrease. What do you guys at the back think? Okay. Actually, typically, in this country and most temperate countries, as the discharge increases, the concentration decreases. Okay, you've got a process of dilution. Right. But if you think about it, that relationship tells you an awful lot about what's going on in the catchment. The catchment is the area that attracts the rain and gets into the river. And what's going on? What goes on in the river is actually an integration of a lot of information. The information has been collected across the whole catchment. You get information about the whole catchment by looking at what's going on in the river. And that's why it's a source of research interest. There's information in there, but you need to try and extract it somehow. So, as I said, in temperate countries, you get a dilution effect. You get more rain going in, the concentration of solutes goes down. That must mean that the rate that the rain falls in is faster than the rate at which the rocks can weather. It's faster than the rate at which the solutes can be produced. Some of you from different countries, I'm guessing, I can't really tell, but I'm guessing. Can you imagine a place where you might have the other relationship, a different relationship where you don't get dilution? Probably earth scientists might be the best people to ask about this. Where would you need to be to have a relationship that wasn't one that was dominated by dilution? It's not something to do with the weather, it's to do with the catchment materials. Like we're saying, the reason you get dilution is because the rate at which the rain falls in is faster than the rate at which the rocks dissolve. So it needs to be somewhere where the rocks are pretty soluble. So all the people that are from Iraq, right, if you were to get very, very heavy rainfall in the desert in Iraq, it doesn't happen very often, then actually the rocks there, there's a lot of gypsum, very, very soluble rocks. You've got some possibility that actually the rainfall and dissolution of rocks can keep pace. Okay, but typically that doesn't happen. Right? And the less weatherable the rocks, then the bigger the dilution effect. So we're starting to put together some ideas, some models of what we think might happen. We've got this model of, well, if the rain falls on the rocks which aren't very weatherable, then we'll get a dilution effect. The data that you've got in this exercise is measuring the total solute concentration in the river. So that's all the materials dissolved in the river. What I was saying a few minutes ago was actually the source of the solutes in rivers. They're not all from the same place. They're not just from the rocks. You've also got a source of solute from the atmosphere. The largest component of solute delivered from the atmosphere is often the hydrogen ion concentration. Okay, the acidity of rainwater is about 5.65 because it's got carbon dioxide in the atmosphere dissolved in it. So when you're delivering rain into a catchment, you're also delivering hydrogen ions. So you're getting hydrogen ions delivered, and you're also getting cations, positive ions, dissolving from the rocks as well. You've got two different sources. What would happen to the hydrogen ion flux? If you get more rain coming into the river, if you could just look at hydrogen ions, not all of the ions together, what would happen to the hydrogen ion flux? As you have more rain going into the river, with the hydrogen ion concentration, what would happen to it? We said that the base cations, which are the ones that come out of the rocks, so the calcium, magnesium, potassium, which typically things that come out of the rocks, when you get more water going in, they tend to be diluted because they can't dissolve from the rocks quick enough. But we're saying actually you get solids coming from two different places, you get from the atmosphere as well. What's the effects of extra rainfall on the hydrogen ion concentration?
It'll increase.
The concentration. Well, it would stay the same, wouldn't it? I mean, it's coming in the rain. It's the hydrogen ion concentration in the rain, so it should stay the same. For the base cations, you would expect to see dilution. For the hydrogen ions, well, if they're coming in the rain, then however much comes in, it's going to be the same. So you'd expect them actually the hydrogen ion flux to be the same. The point is, though, you can separate these two things out. Now, this exercise is taking you through that, so it's building that model up. We've actually sort of worked out a bit already. So first of all, it's this.
Since if rain's acidic and it's coming into the river,
Yeah.
so that river would increase in acidity.
Why would it increase? Because it's the rain.
Yeah.
The river would be as acidic. How could it be more acidic than the rain?
Right. Okay.
Yeah?
So it's not. So the river's acidic as well. It's just as much as the rain.
Yeah, that's the point. I mean, the river's made out of rain,
Right.
and so if you get extra rain, it's not going to change, is it?
If it's all come from the rain, obviously, but if some rivers are.
Yeah, but we're talking about the addition of extra rainwater into a river that's largely rainwater, it's going to be the same. Now, the reason why you're having a little trouble with that is because some of you probably know that actually when you get a rainfall event, then the pH in the river does actually go down, the acidity does increase. But it can't be because there's extra acidity in the rain when it rains. It's not that, is it? So why does the acidity increase? Because the water doesn't have time to actually interact with the rocks and weather the rocks, and therefore that's what lowers the pH normally. So when you get the rain going in, you do get a dip in pH, but it's not because there's an increase in acidity in the rainwater itself, but it's the interaction with the rocks doesn't happen as quickly. It doesn't happen quickly enough, so you get more hydrogen ion going in. All right. So the starting point there with this exercise is you've got the concentration of all the solutes, and you're going to plot them against discharge. And the idea is for you to work through building up a model of what might go on. And the starting point really, is what you were saying, which is that you would expect there to be some sort of dilution. Now, you need to think a little bit further about how's that going to manifest itself in terms of the relationship between discharge and concentration. If we know that the concentration is going to decrease with discharge, right? So if you imagine that as a straight line, then that means at a certain discharge, the concentration is going to be 0, and that doesn't happen. Okay, you can't make the concentration go away. So your first attempt to come up with a model, if your first attempt was the linear relationship between concentration and discharge, a negative, right, what you picked up on is a negative relationship. Yes, there's a negative relationship between concentration and discharge. Is it linear? Well, think about it. It's going to cross the x-axis. It can't be linear, can it? Because you can't get 0 concentration, how much you dilute it. So you need to work out what is the function for dilution. Does anyone know? What's, it's a reciprocal relationship, isn't it? You can think about this yourselves. If you're making yourself a glass of Ribena, how much water you put in it, the Ribena never goes away. All right? But think about the relationship between concentration and volume. The relationship between concentration and volume is that the concentration equals 1 over the volume. So it's 1 over. 1 over is a reciprocal relationship. And if you want to plot a reciprocal relationship as a straight line, then you need to do a double log plot. You need to log both of those. You need to log the concentration and you need to log the volume. So if you plot your figure on log axes, if you have got a dilution going on, then you should get a straight line. So that's the test of your model. You can test how good a straight line you've got. The way that you test how good a straight line is by using your Pearson's product moment correlation. So you can see how good a straight line you get. This exercise then takes you through that process. First of all, plotting it without logging it, then logging it. All the time you're improving the Pearson's product moment correlation, you're improving your model. And then the next step is to recognise that the relationship changes over time. And this is really, really important, again, to lots and lots of modelling issues. You find out the relationship between concentration and discharge is time dependent. And you can imagine this. When you get a discharge event, the discharge goes up, the solute concentration goes down. When the discharge is going up, so say we've got 50 litres a second on the rising limb of the discharge curve. If we move across to the falling limb when it's decreasing, and we've got 50 litres a second, and we read what the concentration was. On the rising limb, the concentration was, say, 20 milligrams a litre. On the falling limb, at the same level of discharge, 50 litres a second, what do you think the concentration is going to be? Higher or lower, or the same? First thought is it would be the same. You know, if you're thinking you're going to get a straight line relationship, then every time you get 50 litres a second, you always get the same concentration. And that would be a relationship that's not time dependent. But I told you it is time dependent. The fact is that most likely, if it was 20 milligrams a litre at 50 litres a second on the way up, on the way down at 50 litres a second, it might be 15, it's less. And the reason for that is because before the discharge went up, solutes had been stored in the system. So there was solutes available in the system. By the time you've had a high discharge, there's lots of water been running through, the solute's no longer available. It's not weathered fast enough from the rock to replace the solute that's been washed out. So the relationship between concentration and discharge is a time-dependent relationship. And some of you may not be interested in rivers. However, the general point about recognising what time dependence is and how it makes it complicated is the important point to take away. So to improve the relationship then, what you could do is to split the data into two separate times. So you can look at the relationship on the rising limb, that's when the discharge is going up, and look at the relationship on the falling limb. And might see you've got two different relationships but less scatter on them. All the time you're getting more and more understanding about what's going on in the system, about the rates at which solutes are produced. So you can do that, you can work through and see if that improves the model. And then the final thing is this idea of separating the solutes out. What you're doing to start with is looking at the solutes all together, but actually the solutes have got a different provenance. Again, this is a word that you should use. The source of the solutes is different. So some of the solutes are coming out of the ground, from the rock, and some of them are coming in from the atmosphere. Largely the hydrogen ions coming in from the atmosphere, and the calcium, potassium, magnesium are coming in from the rocks in the catchment. We've already talked through this. The reality is those two different sources of solutes will behave differently in the face of an increased discharge. If you increase the discharge, as far as the hydrogen ion is concerned, it's not going to change its concentration, because the concentration of hydrogen ion is going to be 10 to the minus 5.65 moles per litre. That's the pH. The pH of rainwater is, in unpolluted air, is 5.65. So that's the rainwater, and that's what we're going into the river. So that's going to be unchanged. The relationship between hydrogen ion and discharge would just be a straight line, okay, of 10 to the minus 5.65 molar. So it should be theoretically. Whereas the relationship between discharge and the concentration of calcium, sodium, magnesium that went from the rocks is going to be a function of how quickly they can be solubilized, they can be dissolved from the rocks. And typically we see a dilution effect, which we've discussed. So when you put them together, what will happen is that you're going to get a scatter on your relationship. Instead of the points all falling on a straight line, there'll be some scatter because you're actually looking at two things that have got different processes behind them. If you can separate the two out, then you can improve the relationship. And you can separate them out because as well as measuring the total solute concentration, this data set's got total solute concentration, but it's also got the hydrogen ion concentration. The pH has been monitored as well. So you can subtract the pH from the total solute concentration and redraw your lines. Okay. Again, it's there for you to do. I'm just trying to get you excited enough to do it because this again is one that you don't have to do. Okay, it's not in the text. There weren't any questions on it. Okay, but how could you not want to do that now? Okay, that's this massive tool, but for understanding environmental systems. Okay, you've got rainwater falling in, and you collect information. That's quite often that's what you're using a river for. Is telling you information about what's going on in the catchment, how weatherable the rocks, and how much solutes move through. So that's why we do this kind of analysis. Anyway, it gives you the chance. What you're doing in this exercise really is devising a model yourself. First of all, your model is, well, I know there's going to be a decrease in concentration. So your first attempt is a linear decrease in concentration. You find that doesn't fit very well, you've got to test the goodness of fit. You think a bit more, you think, well, it needs to be a reciprocal relationship. So in order to do a straight line, you need to do a double log plot. You plot that up, you look at the scatter on that. That's better. Then you move to the next thing, which is separate, recognizing that there's time dependence. Separate it by time. And then you separate it by provenance, by the source of the solutes, all the time improving the relationship and actually getting a better understanding of what's going on in the catchment. And that's the sort of thing that, again, you could do as a project. Okay. But it's not in the test. Right, then these things, we start to get things that are in the test. This is involving more complicated relationships. And this is looking at compartmental modelling, which is a typical sort of environmental modelling approach. These are very simple examples, but though they're very simple examples, they've got all the steps that we're talking about. They also give you the distinction between analytical and numerical solutions as well. So it's very well worth working through these exercises. So the compartmental modelling one is one that you really do need to work. You need to work through. You need to have that one set up in your spreadsheet when you come along to when you come along to the test. Okay, so you need to go do that. But you should do all of these. I feel bad saying it's not in the test. It's there for you to do, to be educated. But you know, if you think that it's taking you more than your allotted 300 hours, then these are the things you can back off on. Okay. The final thing there as well is actually quite short, but it's actually a method of solution. Okay, if you're an engineer, it's very very simple and old hat to you, but if you're not, definitely have a look at it. It's quite simple to set up. It's using a function in Excel that not everyone's aware of, and it's worth doing. Okay, it's a way of getting an analytical solution to a compartmental model by inverting a matrix. And it's something that's good for you to be able to talk about. Okay? If it comes up at an interview or something, knowing why you might invert a matrix and how you might do it. But without going into lots of maths or anything, it's all there for you. But just know the value of inverting a matrix. It lets you solve a set of equations by inverting a matrix. We're not doing loads and loads of that, but just be aware of it and be able to talk about it. So again, you need to do that as well. Okay, right, we can talk about this stuff next time as well, but all you need to do is just be working through the stuff that you've got. Any problems with it, you know, we've got 6 hours next week, we can go through any of those, and then I've got the stuff about the field trip that I want to go through with you as well. And but just work through it, and if you finished it, then do the stuff that you don't have to do, and but there's stuff out for everything. Okay, I can go. Is that all right? Okay, brilliant. Yeah, in the future it's back to the normal times. It's only this week where it's off.